Welcome to the BarleyBin Webinar series. We have today with us Dr. Greg Penner, who is going to be talking to us about refining barley processing for better cattle performance. I had the opportunity to speak at a couple of the cattle conferences the last month or so, and was talking about varieties, which I'll be giving a brief summary of at the end of the present after Greg's presentation. The person to be talking to anybody about feeding barley to cattle. It's not my area of expertise. So that's why we have Dr. Greg Penner here. This is a little bit different format from what we usually have with our BarleyBin Live. But the goal of BarleyBin Live is to have the opportunity to have a one-on-one conversation with barley researchers surrounding a question. So we asked the question to Dr. Greg Penner about what's the best way to be feeding barley and what makes barley an effective and cost-effective and efficient feed stuff for cattle. And so he's going to be talking to us about that throughout the presentation. So after Dr. Greg Penner has talked about the feeding barley to cattle and the quick variety overview. So the varieties we'll be talking about, they're represented by a number of seed companies. We have producing and distributing seed within Saskatchewan, and the Prairies, Cantera Seeds, Alliance Seed, Secan, FP Genetics, and Nutrient Ag Solutions. And we've got some representatives from those companies, or we can connect you with them afterwards if you have specific variety questions. Feed is a pretty important component of the barley marketplace. Though we probably hear a lot more about malt, feed is actually a much bigger portion of the market for our use, reaching almost 70% of all barley produced in Saskatchewan and in Canada going into the feed market. So it's pretty critical that we have those and maintain close connections with the feeding industry. And so SaskBarley chooses its investments based on that outcome of trying to make sure that we've got varieties that are established and ready for feed use, and that we've got the research to support barley use as a feed product. SaskBarley takes a pretty direct approach into funding research. In the previous strategic plan that the board of directors set out, they set a goal of exceeding 65% of annual expenses directed into research. That goal has been met and exceeded for the last 5 years, averaging 71%. So a significant proportion of the levy goes into research. Other portions are going into things like communication extension and advocacy outreach and market development. So that investment in research is leveraged with additional dollars through funding partners, and the goal is to make sure that we're getting good bang for the buck, so to speak, multiplying the levy dollars that come into SaskBarley and getting the most we can out of them. So in that, it goes a lot of it into variety development with several malt varieties, and now some new and exciting feed barley varieties that are coming available. The estimated return on investment for investments made into variety development were calculated at $26 return for every $1 contributed. So it's been a pretty significant return that has been made through those variety investments, and those continue to be made through various avenues like core breeding agreements, cluster, and other projects. But we also invest into feed barley research, and some of that with Dr. Penner here. One of the projects that started a number of years ago will be wrapping up soon, which Greg will be talking about, processing barley grain with variable kernel size. So SaskBarley was one of the funders in that project and leveraged dollars with that. And similar to the one new project that was announced just this year, which we're co-funding with other partners, including the Agriculture Development Fund for fine-tuning dry rolled barley grain processing for finishing beef cattle. This one is delving into some research that looks at specifically at the processing and what the degree of processing should be, because what the industry standard has been was based on some very fairly limited research, and so there's a need to go in and make sure that that is as robust as it can be, because it needs to be a really strong return on investment for feeders as well. So with that brief introduction from SaskBarley and where we're at with our research investments, I'm going to transfer it over to Dr. Penner, and he's going to lead us through a presentation now on refining barley processing for better cattle performance.
Okay, thank you. Can you hear me?
Yep, sounds good.
Perfect. Thanks a lot, Mitchell, and thanks SaskBarley for being such a great supporter of the barley grain research we do here at the U of S. I want to acknowledge a couple of people before I get started. First of all, we're really fortunate to be able to work with some fantastic students, and there's been a number of students that have been trained through these programs as they advance their education and in the end go out into the feed industry to work and hopefully become advocates of barley grain utilization as well. On top of that, there's a number of collaborators, Dr. John McKinnon, who was in our department and has subsequently retired, Dr. Gabriel Ribeiro, who is now our beef industry chair within the department, and then, of course, colleagues at AAFC Lacombe, Dr. Lopez Campos and Dr. Preto, which really have been instrumental for us in the carcass evaluation components. So what I want to talk today about is refining barley processing, really focusing on better cattle performance or strategies really to make best use of that barley grain to optimize performance of cattle. And there's a couple of reasons I think barley grain is used. Of course, we live in Western Canada and our growing season is relatively short, and so barley fits in very well. But when you look at barley as a feed source, we need to recognize a few important characteristics. Now, I have values up, and these values are from Cumberland Valley Analytical, so it's a 5-year average. You can see the direct comparison between barley grain from samples that were submitted from Western Canada. We assume most of these will be grown in Western Canada, but we can't confirm origin of production. It's just where the samples were submitted from. And then we have samples that were submitted from the upper Midwest. So if we're importing US corn, expect that corn grain is likely going to be a little bit different than the corn grain that might be grown here in Western Canada. Couple important things to pay attention to. One is when you look at the dry matter content, we tend to see higher dry matter contents for barley grain. And this is important because we are buying cereal grains on an as-is basis. So if the dry matter content is lower, recognize we're paying for a bit more moisture. We're paying for water that's located within the cereal grain as part of its weight. And so we need to think about that as we're making purchasing evaluations. The other aspect is when we're dealing with corn, we're probably in a situation where we may be requiring some protein supplementation. In many cases with barley-based diets, at least for finishing cattle, additional protein may not be needed. Now, on the starch side, certainly corn has some advantages. We see a lot more starch, about 10 percentage units, almost 12 percentage units more corn or more starch in corn. And it's even a little higher if we look at corn that would be grown in the dominant corn production regions within the US. And consequently, we see that corn has a bit higher energy value, or at least predicted energy value, than barley grain. Now we have to be a little bit careful about looking at those energy values because we know barley and corn have very different structures, and the starch availability within those two different grain sources is tremendously different. So if we think about the availability of that starch from an animal perspective, in barley, the fibrous hull and the pericarp are the major limitations for starch digestion. So once we damage that hull and pericarp, the microbes within the rumen have a pretty good ability to digest that starch. That's not true for corn. So even when we grind corn, the limits to digestion are more how that starch is associated with the protein matrix. And so we really get brought into differing mechanisms of cereal grain processing if we want to maximize starch digestibility for corn. And I'll give you a couple examples of what this looks like. So when we compare that starch digestibility, first looking at the left-hand side of the screen, in this case, we have the same processing mechanism, so dry rolled corn versus dry rolled barley. You can see that barley has higher digestibility within the rumen, which means that less of the starch will escape into the intestine. And in addition to having higher ruminal digestibility, barley has higher intestinal digestibility, leading to a much higher total tract digestibility. So this is where I was getting at. We need to think about more than just the concentration of starch, because the nature of that starch and the availability of that starch is tremendously different when we have grinding or rolling as our processing mechanism. This is also emphasized in the figure on the right. So when we look at a number of processing mechanisms, so we're dealing with dry hull, dry roll, dry ground, all of those are estimated to have a total tract starch digestion for corn of about 90%, and recognize they would be 95 or greater for barley grain. Some people might want to temper roll corn, but recognize that temper rolling corn does not alter its digestibility. And again, this is because the limits to starch digestion in corn is based on that starch protein matrix. It's not whether the microbes have access to the endosperm itself. Okay, so if we want to have a system where we improve digestibility of corn, we actually have to impose processing mechanisms that denature that starch protein association, and ideally may partially hydrolyze or gelatinize some of the starch. So high moisture corn, in this case, it's corn that would be ground and stored much like a silage. So that fermentation process helps dissociate the starch and the protein matrix, allowing that starch to be highly available, and we can get very good starch digestibilities. Or the alternative approach would be steam flaking, where we apply both pressure and steam. So we're adding heat to gelatinize that starch, denature that protein association, again, making that corn grain highly available and the starch in the corn grain highly digestible. Okay, now one of the challenges we have is we need appropriate ways to assess the adequacy of cereal grain processing. And one of the tools I think could be really useful and is maybe a little bit underutilized is the assessment of fecal starch. And the reason this is so useful, or could be so useful, is that fecal starch is highly correlated to starch digestibility. And so you can see two different data sets in this slide here, where you can see when we have very low fecal starch, we have very high starch digestion. And as fecal starch increases, in this case, all the way to almost 45% on a dry matter basis, we see a nice, not linear, but quadratic reduction in the fecal starch concentration. Another study, in this case, they found a linear association, but again, a very high relationship, where high fecal starches generally relate back to relatively low total tract starch digestion. Okay, so why are we even talking about this? And one of the challenges I've heard from the feedlot industry, and we've dealt with it as well on our own operations here at the University of Saskatchewan, is that despite breeders breeding for plump kernels, we're seeing kernel sizes vary among sources of barley. And these variable kernel sizes pose challenges for the feeders as they're trying to process that barley. So for example, we can have differences in varieties, we can have differences in growing conditions, and the ultimate consequence, particularly for larger feeders, is that multiple sources of barley are going to be blended into one bin. And so if you have barley with relatively low rainfall and barley under cooler conditions, you're likely to have different kernel plumpness. And because of that, you'll have kernel sizes that can be tremendously different despite an appropriate bulk density or bushel weight. As a consequence, we can get into situations where we have high fecal starch. And we'll get into why those variable kernel sizes are a problem. But essentially, when we have large kernels, if we set the roller or the processing for the small kernels, we're going to pulverize those large kernels. And if we set the processing severity for the large kernels, we're left with under-processed small kernels. Okay. I think based on the data we're seeing, people tend to err on the side of caution and tend to under-process barley to avoid risk for digestive upset, which can happen if you over-process those barley kernels, if you get too much fines. So this is some survey data we did a while back with Dr. Tim McAllister out at the Lethbridge Research Center. And we surveyed commercial feedlots in Alberta. They had a variety of different barley grain processing mechanisms. There were dry rolled samples, there were temper rolled samples within this cohort. But what we were doing is going into these pens, sampling fresh fecal pats, and trying to understand where fecal starch concentration is. The overall mean in this study, or median, was almost 6%. So we're seeing fecal concentrations that are approximately 6% on a dry matter basis. And you can see we have quite a large distribution with too many samples that are well above 10%. Okay, so this really represents a lost opportunity for those producers as they're utilizing that barley grain. So using some modeling estimates, and in this case, we're estimating a constant fecal dry matter excretion, which probably is not true. But if we apply that, we can see that about 70 grams up to 260 grams of starch can be excreted per steer per day. And if we calculate that back to a barley grain equivalent, we can be up in that 100 to 450 grams per day of barley being excreted. So if we extrapolate that back to barley grain prices, and right now in Alberta, we'd be sitting somewhere between $250 and $300 a ton. That means if we don't adequately process barley, every day those steers are excreting somewhere between 3 cents a day up to 11 to 13 cents under current pricing mechanisms. Okay, so this obviously has a very large economic impact, and helping our feedlot producers assess and ensure that they are processing the barley grain adequately helps to really minimize this lost opportunity in excreted starch. Okay, so, one of the challenges I highlighted is that when we're dealing with barley that has a variable kernel size, if we are going to process to our recommended processing index values, and for dry rolled barley, we're in that 70 to 75% processing index range. At least that's the current suggestions. But we're dealing with diets that are relatively low in silage on the finishing side, relatively high in grain, and there's limited use of byproducts, which means we're feeding dry diets with pretty large variation in particle size. Okay, so we'll have a fairly large amount of fines if we target a constant PI with variable kernel size barley, and then we have other dry products. So we have a sortable diet at an individual level, even when we feed at a pen level for limited refusals. Okay, so just because we're feeding for crumbs or near slick bung feeding management prior to the next feed delivery doesn't mean that individual animals within the pen haven't had the ability to sort components of the diet, choosing to eat what they view as most desirable. So one of the strategies we evaluated to help see if we can mitigate some of the impacts when we're dealing with some barley that is maybe a little bit over processed, a little bit more fines, is to add moisture, add water to that diet. And so in this experiment, we added 0, 10, 20, or 30% water relative to the weight of the barley grain. And we mechanically sorted that diet into particle size fractions. So we have the large particles, and then all the way over on the right, you have the small particles. And this is a really nice graphical or visual explanation of what's happening. But essentially, as we add water, you can see the proportion of those fine particles, the proportion of the dust is getting associated with other components with the diet. So that water or that moisture can help bind those smaller components to be part of the other components of the diet, helping to reduce risk for sorting and hopefully helping to reduce risk for acute digestive upset. One of the ways we evaluate sorting or sorting potential is to use a sorting index. And so this data comes from pen-fed cattle at the Lacombe Research Station. And you can see diets in the dark green that had no water added, all the way to diets in the brown that had 30% of the weight of the barley grain added as water. What I want to highlight is when we look at the pan, which are the fine particles, we can see that adding water really reduced the ability of cattle to sort against those particles. And while I'm focusing on barley grain and fines arising from barley grain, I think there's broader implications for this, because if we're providing mash mineral supplements with feed additives, it's likely that these feed additives are also contained within the fine particles within the ration. So if we want to ensure that all of our cattle receive the dose of minerals, the dose of vitamins, and the dose of feed additives we're targeting, we probably need to think about adding water. And the secondary benefit is that it reduces the ability of cattle to selectively eat components of their diet. A little surprising to us when we see those sorting responses, we did not see any marked differences in performance of cattle. So we did not see differences in ending body weight, and we did not see differences in dry matter intake. Now recognize again, we're feeding the overall pen for limited refusals, so this might influence the sorting potential on a pen level, but we were hoping that on an individual level, we would see some less variation. At least that was partly confirmed when we look at the deviation or the variation observed for marbling. Okay, so we have our Canadian beef grading marbling score, and in this case, the deviation, meaning the amount of variance within the pen, actually decreased as we increased the amount of water. So it does look like there are some benefits. While we might not be affecting overall performance, it looks like we might be improving the consistency of the response for cattle within a pen when we have barley that has a lot of fines and we add additional water. Okay, so that really dealt with how we focus on managing situations if we have excessive fines. The other situation or the other concept is to ask, what can we do to mitigate the risk for fine production? And one of the approaches we were taking was to look at processes where we use moisture prior to the processing event. So this is a study where we reconstituted barley to produce high moisture barley, and we were really interested in understanding kernel characteristics. And while it doesn't look like a lot, when we added moisture to the barley to hydrate them, we saw an increase in kernel width, we saw a reduction in kernel length, and an increase in kernel depth. So what this really means is we were making those kernels a bit more plump, and while they were expanding in plumpness, they were shrinking minorly in terms of length. This is a good outcome from a processing perspective, because as the kernels become wider or larger, we are having a greater ability to make sure that they are all contacted by a roller mill in this scenario. And we can show that response was effective. So when we look at processing index, and again, this is one of the challenges with the processing index, but in this study, we processed hydrated barley to be fine, medium, or coarsely processed. We balanced our fine with our dry rolled, so sitting right in that 70% processing index. But then when you compare the proportion of fines, when we processed that variable kernel size using dry rolled, we had about 8% fines. But when we used moisture-based or hydrated methods prior to processing, we could reduce the proportion of fines down below 2%. So really clear data showing that if we want to be able to process that barley grain adequately, but not yield a lot of fines, even with a highly variable kernel size, we can simply prehydrate to expand the size of those kernels and allow them to be damaged within the rolling process. We've conducted, again, with that survey-based study, analysis of feedlot outcomes based on feedlots in Alberta that are either dry rolling or temper rolling. And this is not really a new process. With temper rolling, we're typically adding somewhere between 15 and 20% moisture, or targeting an 80% dry matter of that barley grain, allowing it to temper for 12 to 24 hours before rolling that barley. And again, the data really shows that when we apply a temper rolling mechanism, we can actually process that barley a bit more severe than we do for dry rolled barley. Not really changing composition as we'd expect, but surprisingly, despite adding a bit more infrastructure cost, adding a bit more management, no real effects are observed for performance of cattle when we look at dry matter intake, average daily gain, or gain to feed, at least in this data set. So while we can manage fine production by hydrating that barley or tempering that barley prior to rolling, we're not seeing very major effects in a number of studies anyway, when we compare that dry rolled or temper rolled barley. We conducted a study to really evaluate that, and part of the concept here was we were seeing a bit more corn coming into Western Canada, and we thought there might be an opportunity to alter how we're processing barley grain, especially if feedlots are considering installation of flaking capacity. So in this study, we fed dry rolled barley, temper rolled barley, or flaked barley that was flaked to a mid flake density or a coarse flake density. I'm showing you here the bulk densities after processing. Our dry rolled was sitting in that 522 grams per liter. Our mid flake was down in that 360 grams per liter, and our coarse flake was in that 450 grams per liter. So when we calculate that as a processing index, our dry rolled barley was right around that 77%, temper rolled close, but a little bit higher, almost at 80%. And then our mid flake and our coarse flake were at 54 and 68%. Okay, so when you look at processing index, we're probably getting a little more aggressive in this study for our flake treatments. But at this time, there was really very little data available on flaked barley. What we did observe were some very interesting responses where, relative to dry rolled and temper rolled barley, coarsely flaked barley did not differ in terms of final body weight for those cattle. However, when we fed a more aggressively flaked barley, we actually had a reduction in final body weight. So a negative effect of over processing that barley grain. That was really driven by changes in intake. So when we coarsely flaked, we had a numerical but not significant reduction in dry matter intake relative to dry rolled and temper rolled. But again, those cattle fed that aggressively processed barley, aggressively flaked barley, had a significant reduction in dry matter intake. And that reduction in dry matter intake drove a reduction in growth, so a reduction in average daily gain, leading to lower final body weights. Of course, when they eat less and grow maybe not so much less, we could have improvements in feed efficiency. And that's exactly what we found in this study, where when we look at the flake treatments, we actually have about an 8.5% improvement in gain to feed over dry rolled barley. Probably what's most important is to compare the differences between the coarse and the medium flaked barley. Whereas with the coarse flaked barley, we actually didn't have a change in carcass weight. Whereas with the over flaked barley, the medium flake, we had about an 8 kilo reduction in carcass weight. So certainly it really shows us that there might be some opportunities with steam flaking with barley. But if we get too aggressive, we're likely going to see negative implications. The other side of that, and helping to explain that improvement in gain to feed, is probably in association with starch digestibility. So we were using commercial sources of barley grain in this study. And again, we blended a whole bunch of sources of barley grain to prepare our treatments. And as a consequence, we dealt with barley grain that was adequate in bushel weight, but had highly variable kernel sizes. And you can see that the fecal starch concentrations for our dry rolled and our temper rolled barleys were very high, in that 14 to 18%. Whereas when we flake that barley, again, adding steam, which should increase the plumpness of the kernels prior to processing, and then again, with that steam, we don't create the fines, we can actually process that barley a bit more aggressive, increasing utilization. Now, we need to be cautious. Remember, the medium treatment had challenges in terms of performance outcomes. And so we have to be careful that we are not over processing barley when we're dealing with steam flaking conditions. Okay. Again, showing similar data. If we look at shrunk final body weight, over processing, over flaking, too small or too fine of a flaking density results in negative performance outcomes, both from a final body weight and a carcass weight basis. Okay. We did not detect differences in yield or quality grades, but certainly when you get an 8 kilo reduction in carcass weight, that's a significant financial penalty. Okay. So this really led us to do a series of studies to try to understand optimal processing characteristics for flaking barley grain. And in this case, we use 7-hour starch digestibility as our indicator. I would argue it's not a good general indicator for barley. We're able to see carryover effects of the treatment, but for barley, really particle size is the limit for starch availability, not more incubation or intensive measurements. Okay. So we looked at a number of parameters in this study. We looked at the conditioning time. So we exposed that barley to 5 minutes of steam conditioning, 20 minutes of steam conditioning, or 35 minutes of steam conditioning. And we found there was no effect of steam conditioning time on the digestibility, 7-hour digestibility of that barley grain. And then we looked at the flaking density, our high, our medium, or our low flaking density. And a low flaking density means a more extensively processed flake. So you can see examples of the flaked barley in the pictures here. This would be our coarsely flaked or high flaking density. This would be our low flaking density, which means it has less weight per unit volume after flaking. Okay, so you can see a much flatter, much more extensively processed barley grain. What we did see was there's a very clear response for increasing 7-hour starch digestibility with flaking density. And when we combine this with performance outcomes, our recommendations are to achieve somewhere around that 450 grams per liter for flaking density for barley grain when we're steam flaking. So the point I want to bring up is we have very different flaking requirements when we're talking about flaking barley and flaking corn. We're going to use really the same temperature treatments because we're using a similar steam chest, applying steam somewhere between 95 and 105 degrees Celsius. With barley, we can flake at atmospheric temperature or atmospheric pressure. So we only need to apply approximately 1 atmosphere. Whereas with corn, we enhance starch gelatinization by applying that steam under pressure. Now that changes the boiler requirements, it changes steam chest requirements, and in some provinces, it changes the requirement to have a steam engineer on site when operating the boiler. Another very large difference is the conditioning time. So for corn, there's no benefit of conditioning beyond 30 minutes, but as you condition from 15 to 30 minutes, you see increased starch gelatinization. With barley, we showed that there was no advantage of conditioning beyond 5 minutes. So what this means is that if you're building a new flaker and you're building it to capacity for barley grain, you could have a much smaller boiler and a much smaller steam chest if you're processing barley. If you're building it for dual purpose and you want to be able to process corn and barley, recognize you can have a much faster throughput of barley grain than corn under the same processing infrastructure. In both cases, we're adding somewhere around that 17% up to 20% moisture. So there's a benefit if you're custom processing and selling that grain to a potential client. But again, our flaking density is going to be completely different. With corn, we're looking at flaking densities of 310 to 360 grams per liter, whereas what I'm going to show you again with barley, we're targeting really that 450 grams per liter. Once you get beyond that, we expect we're going to see some pretty negative responses in terms of feed intake and performance of cattle. Okay, for corn, one of the factors that they may want to evaluate for adequacy of processing is the degree of gelatinization, and really targeting 65 to 85% gelatinization of that starch. Whereas for barley, that's an irrelevant test. Again, we don't need to break that starch protein matrix for barley grain. We really just need to disrupt that hull and pericarp to expose the starch for microbial digestion. Okay, so the whole point is that when we're flaking barley, we need to make sure we are flaking it for conditions representative of barley and not applying corn metrics to that barley grain flaking process. Because in the first study, we did not well balance processing severity across all processing mechanisms, we conducted another set of studies where we were making sure that severity of processing for dry rolled, temper rolled, and steam flaked barley was all at a constant processing severity. So we used processing index as our indicator, and we targeted 70% in this study. Again, what I want to highlight is when we impose those moisture-based treatments, we increase the geometric mean particle size of the processed product. And utilizing metabolism-based studies with ruminally cannulated cattle, we can show when processed to the same severity, we don't see any differences in ruminal pH or the duration of time that pH might be depressed below 5.5, which we would use as an indicator of rumen acidosis. We did see, however, improvements in terms of fecal starch or starch digestibility and a reduction in fecal starch when we applied moisture-based processes. And we think probably what's happening is when we have these larger geometric mean particle sizes, we're seeing larger particles stay in the rumen longer rather than pass out of the rumen more fast and maybe be fermented partly in the large intestine or excreted in feces. So we're starting to think more about how particle size of that processed barley influences retention time in the digestive tract and also influences overall nutrient utilization. In this case, it looks like both temper rolling, but particularly steam flaking, has a positive response to improve that starch availability. Okay, so we then took these same treatments, dry rolled, temper rolled, and steam flaked, and we fed them out to cattle in pens at the Lacombe Research Station. So the diets were essentially equivalent across all treatments. All we did was substitute the type of barley grain processing. And for this study, all of the barley grain originated from the same source. It was all processed at the same mill using the same equipment, and we targeted a processing index of 67%. So we're controlling the mill, we're controlling the barley grain source, and we're making sure the severity of processing was constant across all treatments. Again, not surprising, we saw the same thing. When we apply moisture prior to processing, we do reduce the fine particles. We reduce the proportion of particles on the 1.18 millimeter sieve, and we reduce the particles that would really be dust as they pass through that sieve. So again, it's showing we're producing a product that has larger particle size and less fines within that product. In this study, we actually found a numerical, a tendency for an improvement in final body weight and some very small but numerical improvements in feed intake and for carcass adjusted gain. So it looks like flaking may actually have a positive growth response relative to the barley grain utilized in this study. Okay. Surprisingly, we saw higher fecal starch, but I'm not really worried about this fecal starch concentration. Generally, we would use somewhere around 2.5 or 3% fecal starch as an adequacy threshold. So if we are below 2.5 or 3%, we would assume we are getting a very high starch utilization. And all the treatments in this study were below that 2.5% fecal starch. So while we're picking up differences between the processing methods, what we are suggesting is all of the treatments had good utilization of starch. And so performance responses are more about where that starch is probably digested and impacts rather than efficiency of utilization. One of the really interesting aspects we did in this study is I had Cassie Delver, who was a master's student in our group, evaluate the rumen for damage. And so she evaluated post-mortem, of course, the rumens. After emptying them and washing them, she evaluated the rumen papillae, so the absorptive structures, for clumping. She evaluated redness of the papillae, indicating signs of inflammation, and areas of lesions, whether those were active lesions or areas where there were no longer papillae because of previous damage. And what we saw was that papillae clumping as evidence for papillae damage was much higher in the dry roll than in either of the moisture-based processing approaches. And then when we look at redness as an indicator for inflammation, it was higher for the dry roll than it was for our steam flaked barley. So again, while we might think that steam flaking generally increases starch availability, when we process barley grain using steam flaking to a processing or a flaking density of 450 grams per liter, which equates very close to 70% processing index, 67 in this study, we can actually probably suggest that we don't have as rapid fermentation. And again, it's likely because we have less fines entering the rumen relative to that dry rolled barley grain. In this study, we did not observe any statistical differences in terms of treatment responses, but I do want to draw your attention to hog carcass weight. I think in this study, we were a little underpowered because we have quite a large numerical increase in terms of carcass weight for either temper rolled or steam flake barley relative to that dry rolled barley. So when I start seeing almost 8 kilos difference in carcass weight, even if we can't pick it up statistically, biologically, that is a very large response. And it looks positive from a temper rolling and steam flaking perspective. Now, again, this could be explained by lower rumen damage, particularly in the steam flake treatment relative to the dry rolled treatment, because when we start having damage to those rumen papillae, their ability to absorb nutrients across that epithelium is diminished. And when we have inflammation, nutrients that should be diverted to promote growth and maintenance of animals is really diverted to support the immune response to control that inflammatory outcome. So these would help provide suggestions that if we adequately and coarsely flake barley, we may actually have better utilization outcomes relative to dry rolled barley when processed to the same severity. In this study, we didn't see a lot of issues with liver abscesses. In fact, most of the livers were clear of abscesses, and we could not pick out differences in terms of severity of liver abscesses. So it's unclear why we can see differences in terms of rumen damage, but they don't necessarily translate to differences in liver abscesses. So really wrapping that up, when we compare barley and corn, we know that barley is going to contain a lot more protein and contain more fiber, but will have less starch than corn. And that changes our dietary approach for inclusion of barley or corn into finishing diets. One of the challenges that we have been dealing with is that when we're combining many different sources of barley, we result in situations where we may have variable kernel size. We've shown very clearly if we use moisture-based processing mechanisms, whether that's temper rolling or steam flaking, we can really reduce the impact of that variable kernel size and have quite good performance and quite high starch utilization. We know that starch in barley is much more available than it is in corn. And because of that, we need to think about flaking very different for barley than we do for corn. I gave you some examples of what our current recommendations are when we're looking at flaking recommendations. Okay. The other thing I think we need to pay attention is we need better assays to assess starch availability beyond fecal starch. And the reason I say this is because by the time we get to fecal starch, we've already lost that opportunity. Or if our fecal starches are perhaps too low, maybe we're getting into a situation where we could be having long-term negative impacts on those cattle. So really having an upfront mechanism to assess the adequacy of that starch availability before we feed it to the cattle is really important to help feedlot operators monitor processing adequacy. With that, I hope we have some time for questions. Mitch, I'd again like to thank SaskBarley for all their support. NSERC through the Alliance program has been fantastic, and we've really been able to leverage that SaskBarley funding on a 2-to-1 basis with NSERC. And again, some of the work was funded through the Saskatchewan Ministry of Agriculture through the ADF funding program in partnership with SCAP. And thank you to Cargill Meats for allowing us to gain access to the slaughter facilities and evaluate carcass and liver outcomes.
Thanks very much, Greg. Very much appreciate it. And I think that's a really good overview of the work you've been doing. Yeah, we'll get into some questions, but before we do that, I'm going to do a really quick overview of how we get to the feed barley. I know obviously we have some malt that gets redirected into the feed part of the value chain, but there's some really solid feed barley varieties that are coming out or have become recently available, and I want to highlight those just briefly. And we do have
or feed bunks icing up. but there has been some concern expressed over that. When we look at the data, I think if you bring that moisture content somewhere into that 65 to 70% on a total dry mat or total diet basis, it's probably enough to really reduce that sorting potential within the diet. Another question was, how practical is it to measure fecal starch and adjust accordingly? Um, Fecal starch isn't actually that difficult to assess. We have a number of nutritionists that are utilizing fecal starch as part of their routine diet evaluation already. And we've been doing it a lot in a number of our survey-based studies. In fact, Dr. Gabrielle Ribeiro is running a large cluster project funded through the Beef Cattle Research Council, where they are evaluating fecal starches for quite a few feedlots across Canada, and hopefully we'll have some fecal starch data coming out of that pretty soon. The main characteristics we want to think about is we're trying to target enough fresh fecal pats that we have a representative sample of the pen. So typically we're looking for at least 5 or 6. We want to make sure that we're not contaminating that fecal sample with straw or material from the pen floor or other contamination. So we want to make sure that it is truly feces. And there are a lot of really good calibrations for NIR analysis. Now, we still need to have the sample dried, but we can ship them off to labs and they can evaluate the starch concentration at a relatively reasonable cost, at least when you think about the lost opportunity if we have high fecal starch concentrations. So I think it's something that can be done. It's not something that will be done daily, but as a outcome to evaluate adequacy of processing, I think fecal starch right now is probably the best tool that we have. Now, there's 2 related questions. One about pre-screening barley to get rid of the small kernels before processing, or finding a way to get rid of the dust after processing before delivering it to the bunks. And I think, there's been a fair bit of work looking at size separation of barley and then precision processing based on the kernel size. And that works really well, but logistically, it's quite challenging. So if you think of a 10,000 head feedlot as an example, would need about 100 ton of barley every day. So if you are going to be screening and then segregating that barley and then adjusting the roller mill to deal with that kernel size, it becomes a logistical nightmare. And I think that's really why it hasn't been adopted, despite seeing some potential positive outcomes. The other side of that is getting rid of the dust. Unfortunately, the dust has a lot of the nutrients. And we're feeding barley for energy. We're feeding barley for starch and a little bit for protein. And unfortunately, those components tend to be concentrated in the dust. So I don't think we want to remove the highest density of nutrients. Rather, I think what we're trying to do is manage processing to limit risk of excessively processed barley and control risk for digestive upset.